Welcome back. I've noticed that videos on reloading technique and load development are far more popular than the other ones, so I'm going to be doing more of those. If you are using or planning to use a mandrel setup to help control your neck tension, you are in luck. Today, I'm talking about how to get the most consistent bullet seating forces when using a mandrel to expand necks. Before we begin, we have to acknowledge a simple fact. There are more ways to measure neck tension than any of us can possibly count. So for the purposes of this presentation, I'll make the following distinctions. Neck tension in this presentation is considered the amount of force placed on the circumference of the bullet bearing surface by the neck with the bullet seated. In other words, how tightly the neck is squeezing the bullet. It only results from the interference fit between the sized neck and the bullet. We'll get into that a little later in the video. Second, neck friction is how hard the neck materials drag against the bullet when pressing the bullet into place, like this. Bullet seating force is the gauge force from a 21st century hydro press, K&M seating press, or amp press. It doesn't matter how you are measuring. This is about making it come out more consistent. Let's apply some common sense first. If we add lubrication to the inside of the neck or outside of the bullet, our seating forces will be reduced. That doesn't actually change the tension applied by the brass neck in any way. The bullet just slides easier with lubrication. Now, if this is new information to you, you might need some more life experiences. From there, we need to conceptualize something. No matter what process is used, differences in brass, the lubrication, or the bullet diameter will affect the seating force, and ultimately will affect any tuning you do with neck tension. Let's start down the path of how to get really consistent seating forces, because that is the best indicator we have of the quality of our brass preparation. Before we expand the necks, let's make sure we have properly trimmed and chamfered, or is that camfered? Either way, our brass. Once that is done, you should have a smooth transition from the taper of the chamfer to the inside diameter of the neck. If you have any concerns about burrs, I found that spinning the mouth of the case against a piece of triple-aught steel wool does a nice job of smoothing things out. Don't go do that just yet. We need to decide how big of a bushing to use, if you're using bushing dies that is, and trimming typically gets done after sizing, so hang on. Before we can figure out how to properly expand the necks for the best results, we first have to understand a little about the metal itself. I know there are some material scientists and mechanical engineers out there just waiting for a good explanation of the forces involved. I hate to disappoint you, but I'm going to give a vague generalization here, just to give a part of the why behind the what. Back to the brass. Metals, when exposed to forces, respond to those forces by changing shape, colloquially referred to as flexing or bending. When we size brass, we use the terms sizing and spring back. Let me draw a fictitious stress-strain diagram for you. First, we put in our axes. Next, we label them. Stress on the vertical axis can be thought of in terms of the physical forces we apply, and strain can be generally thought of as the movement of the metal in response to the stress. Now, I'm not an artist, forgive me for this, but here is a diagram. It doesn't represent any specific metal and is just a napkin drawing. As stress is applied, initially the metal doesn't move a whole lot. When we get to a certain point, the metal will start moving more for a given increase in stress. The stress will peak and then let off some, probably a little less than shown. It's exaggerated here for the sake of my artistic abilities. After a short reduction in stress, and not always, the stress will again rise some, once again probably not this much, before retreating again. Then it falls off a cliff when the metal fractures or breaks. I've seen a few conversations online about yield on brass cases, so let's go ahead and label that yield point. It's right here at the top of the first peak. Yield point can be considered the point at which the metal first takes on a detectable permanent change in shape. In the case of our cartridge cases, going past yield during bullet seating can be identified by having the necks larger after you pull the bullet back out than they were before you put it in the first place. That leaves us with two major areas of the diagram to consider. The first is the elastic range. Forces applied within the elastic range will result in a 100% spring back. The other portion is referred to as the plastic range. In that range, the metal will still have some spring back, but will also permanently deform from the forces. Anyone that has sized case necks with a bushing die has experienced this for themselves. The inside of the bushing is smaller than the resultant neck diameter, but the neck diameter was also reduced some by the bushing. So what does this have to do with getting consistent neck tension? Let me draw you a circle or target here. This is where we need to be working the brass when we expand with a mandrel. Notice that we are a little way from the yield point. That is by design. If we are too close to the yield point, we run the risk that variation in brass properties, neck thickness, or other factors will result in some pieces ending up with a different inside neck diameter from others, because we don't move them enough to force all the cases to change size permanently. My first piece of advice here is simple. Get the inside of the neck small enough to ensure you are changing the outside diameter of the case by at least 1/1000th of an inch when you expand, more if your cases are work hardened. You see, work hardening of the case will result in a higher stress required to achieve yield. It will also result in more spring back after the metal yields. That is why I anneal my cases after every firing. It aids in getting the inside neck diameter I want for my size cases when I expand them. That is a great segue to my second piece of advice. Whatever you do, either work harden all of your cases together equally or anneal them all the same. But make sure you don't create your own problems through annealing in a cavalier fashion. There is also a tip in here about expanding work-hardened cases. When expanding them, you will likely need to expand more than 1/1000th of an inch. I've had to size work-hardened cases down to 2/1000ths below the intended inside neck diameter to get the expansion process to work correctly. And then how much difference should you have between the mandrel diameter and the bullet diameter, I hear people asking? Well, I use 3/1000ths of an inch for my 284, mostly because I turn the necks and they're pretty thin. Let me put that aside for a moment. We'll circle back to it. My last piece of advice is to get the friction inside of the neck consistent. I lubricate with NeoLube number 2. Others use Johnson's paste wax. Similar results from those products can be had by simply brushing the inside of the necks. When I do that, I just use a bronze bore brush, but I don't do it that often, so if you have a process you'd like to share for neck brushing, leave a comment below. One thing you do not want is perfectly clean brass on the inside of the neck with nothing between it and the bullet. The friction forces can be quite high in that case and very temperamental. Now that we have super consistent inside neck diameters and consistent inside surfaces with no burrs at the mouth and consistent materials properties, it's time to start seating bullets. When I seat bullets, it isn't unusual at all for me to seat 100 bullets and have a total variation of 10 psi on my 21st century hydro press. What does that translate to on a target? Honestly, I don't know. I've tested several times and whatever effect there might be gets lost in the noise. If anyone is curious, my typical seating pressures average 25 psi on that 21st century press. Now it's time to talk about how much the bullet should be expanding the neck during seating, or what size mandrel to use. I've seen other shooters get good results with anything from 0.5 to 0.5 difference. One thing I do know is that I want to yield the brass again during seating. Remember our diagram? If we leave the bullet on that initial steep uphill slope, we run the risk of having wild deviations in the forces holding the bullet. Likewise, if we have a very small interference fit, say 0.5 of an inch, a plus or minus of 2/10,000ths in our neck inside diameter would result in a plus or minus 40% of our interference fit value. If we applied that same plus or minus to a 0.003 interference, we're looking at a much smaller percentage of our total interference, a little less than 7%. Now, I tip my hat to anyone that can expand next to a 0 tolerance. I certainly can't. It's not unusual to see 2/10,000ths variation in almost any process having to do with sizing brass. If you haven't heard me say it before, I'm an advocate for building processes that serve us, rather than ones that make us slaves to measuring everything. Now, this presentation got far wordier than I intended, so let's do a summary. In summary, make sure you are expanding the brass enough when using a mandrel. Keep your brass properties consistent and ensure you have consistent inside neck friction conditions. Last but not least, try some different inside neck diameters and see which one gives you the best results on target. Thanks for watching. I'll see you in the next one.